My talk is based on research in Heinrich Heine University Düsseldorf, together with Hermann Kampemann and Dagmar Bruce. The title was already announced. So what is this talk about? We consider a quantum network connected by sources of bipartite entangled states. Later, we will consider it more formally. And a subset of parties, here they are purple, want to distill a common either conference secret key. We will spend most of the time, but then at the end of the talk, we will generalize it, at least briefly. I will mention how to generalize it to Grinberger-Horn-Zeilinger or GHZ state with the highest possible asymptotic rate. They want to distill as many bits of the conference secret key or GHZ states as possible per round. And we will be interested in two questions. First, upper bounds on the corresponding rates, and second, optimality of a certain simple strategy, which I will tell about. And we focus in this talk on a scenario which does not require quantum memory. So, practical case for near future quantum networks. Since this conference covers not just quantum information, but as we saw from the introduction, that there are other topics. So let me briefly mention the postulates of quantum mechanics, not all, but which I will need. Quantum system corresponds to a Hilbert space. In our case, it will be a finite dimensional Hilbert space. Then a quantum state is a density operator in the Hilbert space that is a Hermitian or self-adjoint operator, positive semi-definite with trace 1. And a particular case, if this density operator is a projector onto a unit vector from the Hilbert space, which will be denoted like this, then this is a pure state, so-called pure state, like this, or in Dirac notation, it's commonly denoted by this, but mathematicians often don't like Dirac notation, so I'll try to avoid them during my talk. So this is Dirac notation, and this is more standard mathematical notation. Then the measurement is a positive operator valued measure. So it's a set of operators indexed by the outcomes from 1 to m, such that they are positive semi-definite. Their sum is equal to the identity operator, and then the probability of the outcome x, if the state is rho, is given by the trace of the product of rho times mx. And the composite system, if we have two quantum systems with the Hilbert spaces HA and HB, then the composite system corresponds to their tensor product. And we will need the operation of partial trace, which maps the operators on linear operators on this tensor product to linear operators on one of the spaces. For example, HA, partial trace over B or over HB. It works like this. So for tensor products of operators, it works like this. Take trace of the B part and times the A part. And this definition is continued to arbitrary linear operators on the tensor product by linearity. Okay, scenario, n parties. And each round or time slot, they obtain a known multipartite quantum state. With a purification, purification means that this state, rho A E, is pure, and if we take partial trace over E from Eve or environment, eavesdrop or environment, then we get this state rho A. And a subset, maybe all parties or just a proper subset, are secrecy seeking. So they want to distill a common conference secret key or a GHZ states. And other parties who are not secrecy seeking are called helpers. Now, the formal definition of the distillable conference key. Take n rounds of our state, then act on it via with a quantum channel. The allowed operations are local operations and public shared randomness, LOSR, followed by arbitrary classical post-processing, PP. So no quantum memory is required, in contrast to the well-known LOCC, local operations and classical communication, which requires quantum memory. Here, the participants must measure their states immediately without quantum memory, but they are allowed to have a shared randomness. And then when they have classical data, then can post-process and communicate as long as they want. So we act with such kind of quantum channels, quantum transformations, and we want to be as close as possible to the ideal state. This means that these are Dirac notations. I promise not to use them, but this is perfectly uniformly distributed secret bit for the secrecy-seeking participants T, uncoupled from the eavesdropper's knowledge E, and also C is a public register of classical communication. Eavesdropper listens to this classical communication, and this tensor product means that his knowledge is uncoupled from this bit. This means that this is a secret classical bit, and this distance, this is a so-called trace distance, and it must be not greater than epsilon, and such a definition. Such a problem was considered in the bipartite scenario by De Wetack and Winter, and in multipartite scenario by, for example, Augustiak and Horodetsky, and also Das, Boimel, Vinchevsky, and Horodetsky. We consider pair entangled network. So we consider not an arbitrary multipartite states, but multipartite states with a special structure when participants are connected by bipartite states, rho E. So our total Hilbert space is the tensor product of all these Hilbert spaces, and Hilbert space of each participants also consists of several tensor factors corresponding with the particle shared, obviously, with another participant. So pair entangled networks. Then distillable key in the bipartite scenario for pure states, it's given by these unknown facts by the entanglement entropy. So take if the state is pure, then take a partial trace from the projector onto this state, and consider von Neumann entropy. This gives the distillable key for the bipartite scenario in the case of a pure state. And in the case of general, maybe mixed state, general state, the upper bound, there are several upper bounds, and one of them is given by the so-called relative entropy of entanglement. The quantum state is called separable if it's a convex combination of such a tensor product projectors of the tensor product vectors. Otherwise, it's called entangled. This is quantum relative entropy. And relative entropy of entanglement of a given state is a minimal quantum relative entropy between this state and the set of the separable states. It can be shown that it's for pure states, it gives precisely the entanglement entropy. And then this regularized relative entropy of entanglement is an upper bound for the distillable key. Now let's go to the multipartite entanglement, and there is a known result by Das, Boimel, Vinchevsky, and Karol Horodetsky. The previous tools are straightforwardly generalized to multipartite case. So let's consider biseparable states where we have not two parties but many parties. But this tensor product means that tensor product with respect to some bipartition, which can be different from for different i's. And if the state is not biseparable, then it's called genuinely multipartite entangled. And the corresponding bound for the relative entropy of entanglement. And the first question I want to consider explicit calculation of the relative entropy. So on the previous slide, we have such a result. So relative entropy of entanglement, but how to calculate it? Yes, at least we have an answer for the simple case of a pure state. Do we have the same result here? Not just to write this formula, but to calculate this relative entropy of a genuine multipartite entanglement, at least for some simple case. And yes, first result, I would like to show that for pure pairwise entangled state, such kind. So if our rho is a projector onto this, E means edges of our graph. Of course, pair entangled network is represented by a graph, and E's are edges. And for such kind of simple state, the relative entropy of genuine multipartite entanglement is given by the total entanglement entropy of the weakest cut of the graph. For example, in this case, consider the triangle network, and in all our examples, just in examples, all edges have the entanglement entropy 1, so Bell states. And for example, consider this cut of the graph, entanglement entropy 1, entanglement entropy 1. So the total entanglement entropy of this cut is 2. And this is then we can the distillable key can be upper bounded by 2. Or consider this graph. In our pictures, green nodes denote the secrecy-seeking parties, and white nodes are helpers. Consider this cut. We have in total, we cut 3 edges with the entanglement entropy 1 each edge. So the key, distillable key, is upper bounded by 3. But both bounds are not tight. So it's a good bound, but it's not tight because it can be shown that in the first example, the distillable key is equal to 3/2. And in the second second example, I don't know the answer. One can calculate, but at least using theorems I want to present, it can be shown that it's upper bounded also not by 3, but by 5/2. So we can have much more tight bounds. And yes, this I want to present the next results. These two theorems about so-called genuine network upper bounds. So previous bounds bound was based on the bipartition, not just cut. These bounds are based on arbitrary partitions, not necessarily bipartitions. Theorem 2 is about pure states, and theorem 3 about general states. So consider P is an arbitrary partition, and a condition that each partition must contain at least one green node, the secrecy-seeking party. Then we count the entanglement entropies of the cross edges, so edges connecting different subsets of the partition, and divided by the number of the subsets in the partition. Here it's equal to 3 minus 1. For general states, it's the same, but instead of entanglement entropy, the so-called entanglement cost is here an entanglement measure for general states, not necessarily pure states. But let me focus. So we have a generalization for mixed state, for general states, but let me focus on this part. Consider again this example. So we consider such a bipartition. The total entanglement entropy of the cross edges is 5. 1, 2, 3, 4, 5. And we substitute into this formula and immediately get the upper bound 5/2 from the previous slide. So these theorems allow us to get tight genuine network bounds. So to distinguish, to find bottleneck structures, not just linear bottleneck structures, so weakest cut, weakest connection, but bottleneck structures corresponding to more difficult, more complicated topologies like triangular and so on. And another problem, so again, we have such a network of bipartite states, and what is the simplest strategy now let's discuss not upper bounds, but strategy, how to distill a secret conference key. And the simplest scenario we can consider, simplest way, is just measure individually all these states, just measure individually. And then we get a classical a network of classically correlated random variables. And it is a very well-known subject in multi-terminal classical information theory, studied by Chisar, Narayan, and the following papers of Narayan and other authors. It's a very well-known field, and we can apply it. Or is it optimal or not? Because in principle, or maybe collective, complicated quantum collective measurements inside each node can give advantage. So my conjecture that no, that the collective measurements cannot give advantage. So this simple strategy is actually optimal for pure states. We focus in this talk on pure states. And I can prove it in the case of no helpers. That upper bound in the previous theorem is achieved by the so-called spanning tree packing protocol, which was discovered in these papers in 2010 and adapted to the quantum key distribution in our recent paper, accepted in physical review, applied. This is example of a spanning tree. I will not talk much about it. So if the case of no helpers, this simple strategy can be shown to be optimal. I want to tell about what is the problem for the general case. In the case of helpers, the way how do we prove our theorem 2 is we need to consider such kind of quantities. So from the results from classical multi-terminal information theory, we need to maximize such kind of correlation quantity, maximize over all measurements, maybe collective, maybe complicated quantum measurements. In this case, in the case of no helpers, these coefficients, weights, lambdas indexed by all proper subsets of our set from 1 to n are such that the expression is the so-called total correlation, but the important thing that it is reduced a sum of bipartite mutual information. This is a crucial point if we have no helpers. Lambdas are so convenient that we can reduce this expression to a sum of bipartite mutual information. And for bipartite mutual information, we have a well-known quantum information theory and so-called Hollywood's theorem. And yes, it can be, it's not hard to show that bipartite mutual informations are maximized by the individual, not by collective, but by individual measurements. And so in the case of no helpers, we are able to prove that, yes, this simple strategy is optimal. But we have no such reduction in the general case. So what can we do? Probably we need true irreducible, so we need to consider irreducible multipartite quantities and need to develop true genuine multipartite quantum information theory, not bipartite standard Hollywood theory. And briefly about the distillation of GHZ states. Yes, this is again Dirac notations, but actually it's a generalization of the Bell state, like a coherent superposition of 0 and 1 in cat notations are simply the elements of the standard orthonormal basis of the Hilbert space C2. And so this is a actually a coherent version. Distillation of the GHZ state is a coherent, quantum coherent version of the conference key distillation. Actually, it's a very similar problem, but a coherent version. But without classical communication, we are unable to distill such a state, but we are able to distill this state. What does it mean? This is GHZ state up to known phase and bit flips denoted by the operators X and Z in the quantum information. Phase and bit flips, which are known. And actually this kind of state, so GHZ up to phase and bit flips, which are known, is sufficient for such problems like quantum conference key agreement, anonymous conference key agreement, secret sharing, multipartite quantum superdense coding, but not sufficient, for example, for quantum metrology or for distributed quantum computation. For these fields, we must have GHZ states in its how to say, pure form. And for these states, it's these bit flips and phase flips are not a problem if they are known, because we can first measure and then do the corresponding flips already with the classical information. And this problem of GHZ distillation also is studied, and lower bounds in the case of quantum memory and classical communication were obtained by Vrana and Christandel and Salik and Winter. And this is a more difficult problem. If we have a GHZ state, then of course we have automatically a conference key. If we measure, if participants measure their qubits, then they get a key. So if we have some upper bounds for the key distillation rate, they are of course automatically valid for the GHZ state. But a result which is non-trivial, but I would like to announce that what about simple classical strategy for the conference key? It can be generalized. It is already not very classical, but it can be generalized to the GHZ distillation case. So so the second result, I want to say that all upper bounds we obtained for the distillable key are also upper bounds for the distillable GHZ. And actually, simple explicit algorithm of GHZ distillation for pure, if we have pure resource states. Of course, for mixed states, everything is much more complicated. We need to do entanglement purification or some other procedures. But if we have pure resource state, pure bipartite states, and want to distill multipartite GHZ states, then all classical procedures can be generalized. So open problems, as I said, optimality of the simple classical strategy in the case of helpers, then generalization to the scenario with quantum memory, with classical multi-round local operations and classical communication. So is it more powerful or not? So my conjecture is that for pure states, not, but I cannot prove it. Probably in order to prove this, we need the genuine multipartite quantum information tools. And also adaptation for distillation of GHZ up to known bit and phase flips without quantum memory for various protocols for near future. I think it can be interesting because many protocols are based on GHZ distillation, and typically it's considered that we have a quantum we need to have a quantum memory, but actually with slight modification, which is sufficient, we can do this even without quantum memory, which can be investigated. So that's what I wanted to tell. Thank you for attention.
Thanks a lot, Anton, for this beautiful presentation. Are there any questions? We have some minutes for discussion, for questions on site, also online. If there is some questions Zoom, Peter, you can tell us. Okay, just from my side, I have a question. So you said the presentation, also in the title, there is this mentioning that quantum memories today are not so practical to consider in real scenarios. For this kind of protocols, I mean,
no. So of course there is active research on developing quantum memory. So hopefully we will have quantum memory in future. But for right now, as far as I know, we don't have how to say don't have quantum memory and yes, it's interesting for near future to consider scenario without quantum memory. What can we do without quantum memory?
So then my follow-up question would be like, if you manage to solve this problem of quantum memories, what are, because in GHZ schemes, you want to create GHZ with different parties. There is this scaling problem sometimes with the number of members of the one that will share the GHZ state. So somehow this is the next problem. No? After memories are solved, what is your opinion on these scaling problems when you have n members?
I think
my question is not clear. So how to overcome the next question after the quantum memories? What is it? Yeah, sorry about my. Is it clear, my question?
So scaling to with the number of participants.
Exactly. What are the main challenges in this regard?
I think that yes, this research, these scenarios is a kind of overcoming the restriction with the number of participants. Because if we have generate a GHZ state directly, we can generate tripartite GHZ, four-partite, but I think not 100-partite GHZ. For if we need to have 100-partite GHZ, we need to start with Bell states or maybe like tripartite GHZ, and then to use such kind of protocols to merge them into large GHZ state. And I think it's scalable to large number of participants. At least I don't consider much the practical issues like noise. I don't know what about this. Probably for a large number of participants, noise will be more important factor. But at least in the ideal, ideal states, it's well scalable.
Oh, thanks a lot. I have a question here from Bulat. Yeah, one minute question.
So I'm a little bit confused. Could you go back to where you actually state the where exactly do you not use quantum memories, and are they in upper bounds? I don't think you have any lower bounds here. Do you have lower bounds? I'm just, maybe I missed them or something.
We don't use quantum memory because we consider actually in on this slide local operations and public shared randomness. So in so they parties have to immediately measure their states. They don't have quantum memory. They have to immediately measure and then already post-process classical information.
Right, but then when you this is for classical task. When you go to the quantum task, when you go to your slide, I think where you had the brief mention of Andreas Winter's result on the what's it called? I'm a bit jet lagged. I apologize for being slow, but yeah, that yes, I mean that basically implicitly requires a quantum memory, I think, if I'm not mistaken, and I may very well maybe.
Yes.
Just in the fact you're constructing a measurement which is what's the word I'm looking for? But it's a measurement that spans all of these systems. Shun, you know what I'm talking about? It's so. I'm just not sure whether one can claim it's nice work, but claiming that it's completely quantum memory free might need to be elaborated more properly, I think, just considering that, because they in those words, it's implicitly assumed that quantum is available.
Yes, in the paper, I actually mentioned in the case of communication. So yes, Salik and Winter consider the scenario with quantum memory. Yeah, I agree. But my scenario is without quantum memory. And for GHZ, yes, actually for GHZ we also don't need quantum memory. Again, all parties immediately measure the system. And one can say that they have GHZ like virtually. So they get their systems, then they measure them. So of course, as soon as they measure, they don't have quantum state at all. But then they can think that they had a GHZ measurement, like in measurement device independent quantum key distribution protocols. So they don't deal with quantum states, but this is equivalent that they had quantum states after they performed all the measurements and performed all necessary bit flips. They can think that they had for 1 second, 1 instant, they had a Bell state, and this is the same. I don't need quantum memory. They immediately measure. Then they communicate all their not all, but some their communication results, perform the corresponding flips, and they can think that they had just had the GHZ state and can use it, the result of these measurements, for protocols like conference key agreement or anonymous conference key agreement. So equivalently, like they had it, like they really had it. That's the point. What I said that yes, precisely for quantum sensing and distributed quantum computation, this approach is not applicable. That's true.
We thank a lot, Anton. Thanks for the discussion.
Thank you.